Hi, welcome to educator.com. Today we're going to be talking about variability. All right, so we're going to start off with just a conceptual introduction to the different kinds of ways that you could measure variability. Then we're going to talk about range, quartiles, and interquartile range. Then we're going to talk about variance and standard deviation. And in particular, we're going to focus a little bit, on the concept of sum of squares. Then we're going to talk about population standard deviation versus sample standard deviation and talk about the differences in their formulas. And then we're going to calculate standard deviation in Excel. All right, let's get started. So let's think about a conceptual way of thinking about variability. There's lots of different ways that you could actually think about variability. So for instance, let me give you this example. Let's say this x right here, right? Let's say this x shown in each of these is the president. Right now, Barack Obama. And so let's say that this is the president. And these are different groups of people that are standing with him at some sort of formal party, right? Formal event. So here we see the Secret Service, and this is how far each of them are from him. Here we see the Supreme Court justices, and they're sort of scattered around him, spread out around him. Here are his cabinet members that he's appointed, and so they're sort of scattered around him. And here are the Tea Party senators. And let's just say maybe that there are senators that don't really like the president as much, right? And so they're sort of seem to be huddled over here, right? Now, which of these groups of people is sort of most spread out from the president, right? Which of these groups of people is sort of closest in, right? Who's closest to the president? Can we describe that with a number, right? Well, there's a couple of ways you might want to think about it. Well, one way might be, just look at the farthest person away from the president in each of these sets, right? So maybe for this, it's either this guy or this guy, right? And get that distance, and maybe that's the distance you need. So for this, maybe it's this guy, or maybe it's this guy, right? Maybe here it's that guy over there, right? Maybe here it's this guy, or maybe that guy. They seem pretty distant, right? Maybe that guy's a little bit farther, right? So just looking at the farthest person in the group, right? That's one way of looking at it. In that case, it doesn't really matter how many people in the group you have, right? So this group has fewer people than this group, but it wouldn't matter if we're just looking at just the one farthest guy in the group, right? That's one way of looking at it. Another way of looking at it is maybe creating a little boundary and saying, how many people are in that boundary, right? So maybe we have this little square around the president, and we just look at how many people are in that square. So maybe for here, if we draw, oops, sorry, my square's sort of crappy, but if we draw a square like that, how many people fall in that square, right? If that was our measure, we would say, oh, this group is the closest to the president, right? Here we have like one person in the square, and none of the other groups have any people in the square, right? And then maybe we could look at different types of squares and see if that changes anything, right? So that might be one way of doing it. Another way of doing it might be to sort of maybe find the area of the border, right? Right? Maybe that's another way of doing it, right? Maybe this one. And that one doesn't seem like a very good model, because that would mean that these people are the closest to the president. But this is sort of an odd group. They're close to each other, but not necessarily close to the president, right? Should that matter in a measure of variability? That's another thing to think about. But probably one that probably comes to your mind is sort of this idea of maybe the average distance of all these guys away from the president, right? So who has the closest sort of average distance, right? Then we also wouldn't need to worry about how many people are in the group because we divide by the number of people in the group, right? And it actually wouldn't matter if they're close to each other or not, right? We just care about distance sort of to the president, right? And so those are sort of different ways that you could think about variability. And so notice that they're all ways of sort of sticking a number on this concept of variability, but you might come up with different numbers, and you might come up with different sort of definitions for what it means to be spread out versus very close, right? So there are some things to think about. Should we be measuring how far they are from the center or how far they are from each other, right? So center is going to be an important concept in variability. So should we measure it from the median, the mode, the mean, right? Does it matter if this group has few or many members? Should that be taken into account? Does it matter what direction away from the president or from that center point, if it's to the right or to the left, up or down, right? And what about consistent clustering? Should that matter, right? So those are some things to think about when we think about a measure of variability. Now, there are lots of different kinds of measures of variability, and we're going to be talking about two sort of broad classes of them that are going to address these questions in sort of different ways. All right. So the first class of measures that we want to think about are range, quartiles, and interquartile range. This is sort of like the idea of just taking the one farthest guy or the one closest guy and looking at that person. And usually these measures of variability are used with median, right? It's usually about measuring spread around a median. So one of the reasons that this is going to be the case is that when we look at range, quartiles, and interquartile range, what we're really doing is taking a distribution and cutting it up, right? Either cutting it up in half, which would be the median, the middle point, or cutting it up into, let's say, quartiles, right? Which would be cutting it into fourths, right, instead of halves, right? All right, so that's sort of the idea, and that's why they're going to be using median as their measure of central tendency. So when we think about range, you actually don't need a central tendency at all. What you need is the minimum value and the maximum value and the distance in between. So you could sort of think of it as the maximum value in the set of x, right? And then subtract the minimum value in the set of x. Right? So if you had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 as your distribution, you take 10 minus 1, and your range is 9, right? The problem with that measure of central variability, even though it's really simple, very intuitive, it's highly susceptible to outliers. So if we changed our set to something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 100, right? All of a sudden, it would be 100 minus 1, and our range would be 99, right? And so just by changing one of our numbers, we could drastically change the range. Interquartile range is going to be less susceptible to those outliers. But before we get into how to calculate interquartile range, we have to learn how to divide that data into quartiles. So let's just look at a sort of simple example. Right? So here, what we would need to do is just divide this data into quartiles first. Since it's an even number, the median would fall in between 5.5, right? And then to divide it further into quartiles, we divide it at the 3, and divided at the 8, right? And so here's the first quartile, the second quartile, the third, the fourth. And because of that, these borders actually have special little names. These borders are called Q1, Q2, and Q3, just to indicate that they are the borders of the quartiles, right? And so first you divide the data into quartiles, and then basically, in order to get interquartile range, you're basically sort of lopping off these guys on the end, sort of like the end of bread or the end of cucumber, like we're just like sort of chopping it off and casting it aside, just in case that there are some extreme outliers, right? So here, what we do is then we take Q3 minus Q1, right? So in this case, it would be 8 minus 3, and the interquartile range would be 5, right? So here, the interquartile range sort of gives you the idea 50% of the numbers falls in this range, right? Because that's 2 quartiles, right? So that's 50% right there. And so that's why it's sort of a nice measure. It's more robust than actual range because it's less susceptible to outliers. It's still pretty intuitive, and it gives you that nice 50% of all the numbers falls in this range. All right, so that's interquartile range, pretty easy. So let's do an example, another example. So here, let's say there are these ages, right? And we want to know what the interquartile range of this is. Well, first it helps to separate them by quartiles. So there are 3, 6, 10 numbers here. So because of that, here's sort of the midpoint, right? So the median, also called Q2, that is 30, right? So that's the median. Here is Q1, and here is Q3, right? So Q1, Q3, right? And in order to find interquartile range, sometimes called IQR, it's Q3 minus Q1. So in this case, it would be 38 minus 20. So our interquartile range is 18, right? So within 18, so here we could just sort of draw that distance of 18. So in that distance, 50% of our numbers fall in there, right? So between 20 and 38. All right. All right, so now we're going to be talking about variance and standard deviation. When we talk about variance and standard deviation, it's really more like, in that conceptual example, that distance away from the president, where we're looking at the actual distance, right? And in statistics, what we call distance away from the mean, the president in this case, is a deviation. We call that a deviation, right? And so what we might want to do is get sort of the average deviation, right? But there's going to be a little bit of an issue. When we get the deviations from the mean, remember the mean is sort of the middle, the value that's in the middle, right? So the amount is actually sort of in the middle of all the other values, right? Some of the values are going to be greater than the mean, and some of the values are going to be less than the mean. When we add all of those up, right, the formula looks like this. So the summation sign, where we take each value in our distribution, x sub I, and take out the mean, so subtract, get that distance away from the mean, that deviation from the mean, right? When we add all those up, where I goes from 1 all the way to n, however many we have in our sample, we basically get 0, right? Because sometimes the value is greater than the mean, sometimes the value is less than the mean. When it's greater, the number is greater than 0. When it's less, the number is less than 0. You add up a whole bunch of positive and negative numbers, you end up getting something very close to 0. So that's the problem, because when you get 0 as your sum and then you divide by whatever your n is, no matter what your n is, it's going to be 0, right? Because 0 divided by anything is 0. And so this is not going to work for us, right? That's not going to be good to have every single average deviation being 0, right? That's not useful. So what do we do? Here we're going to sum the squared deviation. So instead of just summing up all the deviations, we're going to square the deviation and then sum those up, right? And whenever you square it, you get you get a positive number, right? So the sum of squares is always going to be positive. And you get many advantages out of doing this squaring business, and we'll learn more about some of those advantages later. But let's talk about how to write this in notation. So here we have that same idea, that same deviation idea. We're looking at distances away from the mean, right? But we're going to square each of those distances, right? I equals 1 to n, right? Now, just a word about this summing notation. Basically, when you have the summing notation, whatever's here, you need to do this first and then sum up everything in here okay? Sometimes what people do is they sum up all of x sub I first, right? So they sum all of them up and then subtract out the x. But we're not summing the values, we're summing the squared deviation. So you got to get the squared deviation first, right? And each value is going to have a distance, and each of those distance needs to be squared, and then you need to add them up, okay? And then this won't equal to 0 unless all your values are 0 and your mean is 0. But barring that case, they won't usually equal to 0. All right, and this is going to be called sum of squares. And that's often shown by using the term SS, right? And if it's sum of squares of the sample, sometimes you'll see this notation where it has a little x down there. If it's the sum of squares of the population, which you probably won't ever have, it will be SS sub big X, uppercase X. All right. Now we could look at the average squared distance from the mean, average squared deviation, right? And you do that simply by dividing by the number of values you have, right? So when we have the variance of a sample, that's going to be called S squared. That's going to be the variance, right? I'll write it in blue, right? So that's the variance of a sample. That's just going to be SS divided by n, right? Now, the problem with variance is that it's not in the same units as your mean because we've squared all the distances, right? So in order to bring it back to the same units as the mean, it's easier for comparison, what we're going to do is get the standard deviation by just square rooting each side, right? So standard deviation is just S, and that's going to be just the square root of variance. Ta-da, right? So standard deviation is now just the average distance from the mean instead of average squared distance away from the mean. Now, this is going to be for samples, but in order to get variance for the population, they use the lowercase sigma. So for variance, it would be lowercase sigma squared, and for standard deviation, it would just be lowercase sigma. And I'll show you in a little bit how to do that. All right, so now let's take a little bit of time to talk about sum of squares in depth, all right? And before that, there's a little typo on this page, so I'm just going to correct that so that it'll be smooth when we get down here. All right, so let's start from the beginning. Sum of squares is always the sum of squared distances away from the mean, right, of the sample. And the mean of the sample is x bar. That's how we denote it, right? That's the symbol for it. Now, the sum of squared distances away from the mean is going to be the smallest sum of squares than from any other point. You could pick any other number, right? This will give you the smallest sum of squares. Any other number will give you a bigger sum of squares, right? Now, here's the problem. The sample mean is rarely ever the actual population mean. And because of that, the population mean is this any other point, right? It's any other point. So if we had the real sum of squares from the population mean, we'd actually get a bigger sum of squares than we actually have, right? That's a problem. Here's why. Because then that means because we have a sum of squares that's a little bit too small, our sample standard deviation is going to be actually a little bit smaller than our population standard deviation all the time, right? That's an issue. We're always sort of undershooting the population standard deviation. So to correct for this, we're going to divide the sum of squares from our sample by a slightly smaller number than we actually do. Remember, right now, to get S, or standard deviation, we take sum of squares, divide by n, right? That's what we do right now. Well, this won't help us approximate the actual population, right? And so here, we're going to need to divide by a slightly smaller number. Because when we divide by a smaller number, then our resulting answer is slightly bigger, right? So dividing by 5, you're going to get a bigger answer than if you divide by 8, right? And so because of that, we're gonna use that. So instead, in order to approximate the population, standard deviation, right? What we're going to do is use SS divided by n minus 1, right? Because this is going to be a slightly smaller number, giving us a slightly bigger population standard deviation, right? And why n minus 1? Why not n minus 0.5 or n minus 2, right? There's a proof that you could look up online called Bessel's correction proof, and it's a really elegant proof if you have time to look it up. All right. So that's my spiel on sum of squares, but we'll probably come back to this because it's a pretty important idea. All right, now let's talk about the difference between population standard deviation and sample standard deviation. Now, we always want to make inferences from the sample to the population. That's what we really would like to do. And our sample distribution is denoted by lowercase x. Our population distribution is denoted by uppercase X. And we're always going from, in order to make that leap, we're going from sample statistics, right? This should say statistics to population parameters, right? And so we're going to be estimating things like estimating mu from x bar, right? That's estimating the mean of the population from the mean of the sample. And we're going to estimate the sigma, or the standard deviation of the population from S, which is the standard deviation of the sample, right? So sigma is sort of a new notation. Notice that for population, we're using parameters that use Greek letters. And here we're using regular Roman letters. All right, so now let's talk about the formulas for these. So remember, when we talked about mean, mu in this case, and x bar in this case, we talked about adding up all of the lowercase x's and dividing by lowercase n. Here, we added up all the ones in our uppercase x's and dividing by uppercase n, right? So just superficial changes, right? When we talk about standard deviation, here we're going to be talking about sigma, lowercase sigma, or talking about S. All right, so let's actually write down this formula. You could write it as square root of sum of squares divided by n. That's one way to do it. But one thing you could do is sort of think about double-clicking on this, right? Right? Let's say I double-click on it. Then what we would get is you'd see the whole shebang inside. Hopefully I could draw it. Sum of squares really means give me all the square deviations, distances, away from x bar, square all those. And if you want, you could put in I equals 1 all the way up to n, right? lowercase n, right? All divided by n, right? Or if we want to actually estimate, use this to estimate that, we would divide by n minus 1. This is an uppercase S, and I'm going to denote that by using like a little bar there. In order to have this estimation, we would use lowercase s. Lowercase s. It looks just like uppercase s, but I'm not going to put that little handle right there. And in this case, what we would do is divide our sum of squares by n minus 1. And that's our way of estimating from s to sigma, right? That's our estimate. When we talk about the population standard deviation, it's still SS divided by n, but it's uppercase N this time. And when we sort of double click on SS and see what's inside of it, right, we unpack that. Here's what it looks like. It's big X sub I minus mu this time squared, all divided by uppercase N, right? So here are all these formulas. We have formulas for standard deviation of the sample, standard deviation of the population, but we also have this new idea. This is sort of in between this one and this one. It's a way of going from sample information to estimating a population standard deviation. Now, usually we don't calculate sigma directly because we don't have every single value for the population. Usually we calculate small s, which is going to be the estimated standard deviation. And we hardly use this one as well because we don't really care about the standard deviation of just our sample. We really want to know the standard deviation for the population. All right, now let's go on to our examples. Here's example number 1. It says find the mean and standard deviation of the variable friends in the Excel file. All right, so if you get the Excel file that you could download, go ahead and click on friends. We're going to be finding the standard deviation for the variable friends. All right. What would be nice is if we could do everything in Excel. But before we do that, I just want to make sure you understand how standard deviation works. And so because of that, I'm going to sort of have you do it manually first. So in order to do that, go ahead and go to Data, find the variable friends, click on that column, and I'm just going to copy that whole column and paste that right in here. So here I have my entire distribution of friends. And then I'm going to say, Excel, calculate the mean for us. And I'm going to use the function average and select all this nice data right here. Hit enter. And that's our mean, right? Now, that mean is not going to change for anybody, right? Because the mean is just the mean of the entire distribution, right? So I'm just going to put a pointer there. I'm going to say, hey, whatever the mean is on top of me, that's the mean, right? And then I'm just going to copy and paste that all the way down. And so this whole column should have the same mean, right? The reason I'm doing that is because that's going to make it easier for us to calculate squared deviation. We could just use the locked version of mean too. So there's different ways of doing it. All right, so now let's get our squared deviations, right? So deviation just means the distance from each value to the mean, x bar, right? Squared, right? And in order to do the square, we put in the caret and 2, right? And so we hit enter. And here's our squared deviation. Now I'm going to just drag that formula all the way down. And so we have here a whole bunch of squared deviations. Now, we have to sum up all those squared deviations, right? So here I'm just going to put in SS, because that's what we're going to get. And in order to get SS, we just add up this whole column. All right. And in order to get variance, right, or big S squared, right, what we need to do is take SS and divide it by N, right? So I'm going to take SS and divide it by my N. Now, I know here that my N is 100, but if you didn't know for some reason, you could use the function count and just ask it, count how many values there are. Not count if, but just count. Count how many values there are. Should be 100. And indeed, it's 100 because it just moved the decimal point 2 over, right? And so now we could get standard deviation, right, or S. And in order to get that, we just square root our variance. Excel has a function called square root, SQRT. I'm just going to square root my variance. And here I get a standard deviation of 428.64, blah, 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 right? Now, I made you do all that just so that you would understand how to calculate standard deviation. But Excel has a nice handy way for you to do it. So here I'm going to calculate S sort of automatically. Now here we're looking at just S, right? And in order to calculate S, we would do STDEVP, because that's the one where you divide by N. Okay. Ta-da! Oh, right. Standard deviation P. Oh, wait, sorry. I'm finding the standard deviation of all my squared values. That's wrong. I should be finding the standard deviation of my actual data, right? Yeah, so here, because in this method, you actually don't need any of this. I just made you go through it, just so you would learn. All right, but when we calculate S automatically using STDEVP, you see that we get the exact same standard deviation, and we don't have to do any of that mean calculating or calculating sum of squares or variance or anything like that. Now, there's even a way that Excel will calculate for you little s, the estimate of the population standard deviation from the sample. Now, that's the one that you'll be most likely using. And so because of that, I think that might be a good one for us to do. So sum of squares is going to be the same thing, right? I'm just going to actually copy all of this, right? So sum of squares is actually going to be the same thing. But variance is going to be a little bit different now. Instead of dividing by n, we're going to divide by n minus 1, right? And so I'm going to put in 99 instead of 100, right? And then square rooting, that works the same way. Square root of my variance, right? And so now notice that when we divide by n minus 1, my standard deviation is, oh, this should be lowercase s, also lowercase s. Notice that my standard deviation is slightly bigger than it would have been when we just divided it by n, right? And so now let's calculate little s automatically. And Excel always assumes that that's probably what you'll be wanting to do. So it made STDEV, just standard deviation. That default formula is going to divide by n minus 1. All right, so that we see that those two are the same values, sort of a shortcut, right? And so you see, when you automatically calculate it with Excel, you're not going to need to calculate mean or the sum of squares, but it's nice to know where those things come from. All right, so we did that already. Now let's find the mean and standard deviation of the tag photos in the Excel file. All right, so if you click over on data, let's go ahead and grab the tagged photos variables, values, that variable column, and then paste it right in here. It's just easier than going back and forth. And let's find the mean of this sample. So I typed in average, and I want it to average all of this, right? Then I'm just going to say, whatever's above me, that's the same mean. Copy and paste that all the way down. Everybody has the same mean. And then I'm going to get my squared deviation. So it's my value, my first value minus the mean squared, right? And then I'm going to copy and paste that all the way down. Great. Now let's get the sum of squares. And in order to do that, we just find the sum of all these squared deviations. And then in order to find variance, or big S squared, right? Actually, let's just do little s squared, because that's the one you'll be using for the most part, right? For little s squared, we take this sum of squares and we divide it by n minus 1. We could use count. So count all of that minus 1, right? Right? And so, oh, I think I have an extra parenthesis in there. Right? So all of this is in my denominator, and I hit enter. So that's my variance. Now what is my standard deviation? My little s, my estimated standard deviation. Well, all I have to do is square root my variance, and that's what I get, right? And now let's check our answers by using the automatic Excel version. Here, we'll put an STDEV, stand dev, right? Oops, I almost did that again. I want to put in our actual data, our actual values. This is our real distribution that we're working with here. And ta-da! Excel does it nice and quickly for us. We don't need all of this stuff. In the future, we'll just be using this automatic version, but I do want you to know where that comes from. All right, let's go on to example 3. The average number of calories in a frozen yogurt is 250, with an estimated population standard deviation of 30. If 24 frozen yogurts from popular chains were sampled, what would be their SS, or sum of squares, right? Well, here, we know that we don't need the actual values and the means in order to find sum of squares, because we have some of the other pieces, and we could just sort of fill out what's missing. We could figure out what's missing. Well, we know that they have estimated population standard deviation, right? So that's little s, right? And in order to get little s, we know that they added up, added up all of the x sub i's minus the mean, squared that. all divided by n minus 1 and then took the square root of that. We know that that's what they did. And another way of writing that is square root of SS over n minus 1. All right, so let's fill in what we have. They know that the standard deviation eventually is 30, right? So this S is 30, right? And what we're trying to find out is this. We don't have that, right? SS, we don't have that. But we do have n minus 1 because n is 24, right? So 24 minus 1 is 23. So from that, and only that information, we could figure out SS. And in fact, this mean, they've given us this mean, 250, is sort of a red herring. You don't actually need it in this problem. All right, so I'm going to use a little piece of my Excel as a calculator. And here I know I need to square 30. So 30 squared, right? And then I could just multiply 23 to that. So I get 20,700. So my SS is 20,700, right? And I didn't actually need all my values from the distribution, nor my mean. All right, last question. Example 4. This is a conceptual question. Hopefully your tests will test you on concepts. When you divide by n minus 1 rather than by n, what effect does this have on the resulting standard deviation? Well, n minus 1 is a smaller number than n, right? And dividing by a smaller number will result in a bigger answer. And so the resulting standard deviation, S, will be a little bit greater than this S. This one divides by n, and this one divides by n minus 1. All right, so that's it for variability. Thanks for using educator.com.